This is How to Math with Dr. Ian Lundholm. In today's episode, vector spaces, subspaces, and spanning. Today we're going to be talking about vector spaces like all of the spaces that we've talked about so far. Even though we haven't specified it, R2, the coordinate plane, that's a vector space. R3, three-dimensional space, that's a vector space. There are things that behave like vector spaces that we are not going to go into deeply in this course, like set of, all polynomials. That is actually a vector space. I think we watched the first part of this video down in the bottom right-hand corner, abstract vector spaces from 3 blue, 1 brown. We watched part of that video earlier on in this class, but that video is really cool at giving you another different example of what a vector space could look like. In that video, he actually goes into showing you how the derivative can be encapsulated in a matrix. And actually, if you work through finding, eigenvalue pair for that matrix, you actually find that, based on, like an infinite series, like a Taylor polynomial is what you get. You actually find out that e to the x is an eigenfunction for that derivative operator matrix. Super cool. Not necessarily, central to this class, but just another cool way that linear algebra is a powerful piece of mathematics. Okay, so other than that, let's define what a vector space is, realizing that while we are working with tuples of real numbers, there are other things out in the world that can be considered vectors. And what we're doing as mathematicians right now, what we're going to be concerned with today, is talking about properties of vector spaces that should work on anything that behaves like a vector. So, let's get into this. And if you haven't already, go ahead and finish up that abstract vector spaces video from 3 blue, 1 brown. It's on our playlist. Okay, a little bit of notation here. U, V, and X denote vectors. All of that stuff is hogwash. We know that. Here's our first important definition. We're looking at the definition of a subspace here. So I'm going to highlight that. That is the new vocabulary term. And a subspace is a special subset of Rn. A subspace must include the zero vector. It must be closed under vector addition and closed under scalar multiplication. So a subspace always has to go through the origin, and the normal operations of, scalar multiplication and scalar multiplication and vector addition. When you operate on vectors in the space, they need to stay in the space. Here we go. So if we wanted to think about what kinds of things are actually subspaces of R3, the first and smallest subspace would be just the origin. The origin is a subspace because it does contain the zero vector. And if you add the zero vector to the zero vector, you stay in that space. And if you multiply the zero vector by any number, you also stay in that space. And that's the only kind of zero-dimensional subspace of R to the n. The other kinds of subspaces in R3 would be lines through the origin. That would be a one-dimensional subspace. We could have planes through the origin. That would be a two-dimensional subspace. And actually, all of three-dimensional space is a subspace as well because, yeah, when you add three-dimensional vectors together, you stay in three dimensions. And, yeah, so the entire space is a subspace of itself. Not necessarily a proper subspace, but a subspace nonetheless. Here we are in R3 again. This is just an example of a line that goes through the origin. And here we show that indeed the line contains the zero vector and is closed under vector addition. And probably on the next slide, it's scalar multiplication. But yeah, if you've got a space that is just based on multiples of one vector, here we go, multiples of this vector, yeah, whenever you add vectors that look like that together, you stay on the same line. And here's the scalar multiplication version. Whenever you multiply a vector, it stays on the same line of vectors. Yeah. Keep going. Here is what it would look like to verify that a plane that goes through the origin is indeed a subspace. This is one way to define what a plane is using the normal vector. Here's our normal vector n, and here's kind of the set definition of what that plane would be. It would be all of the vectors u that have a dot product of 0 with the normal vector. That's one way to define all of the points in that plane. And then, yeah, another just few steps here. Yes, the 0 vectors in that plane. Yes, vector addition is preserved among vectors in that plane. And yes, scalar multiplication is preserved among vectors in that plane. So, yeah, basically what those are saying is like, if you start off with vectors in a plane and you add them together, you're not going to suddenly hop out of that plane to somewhere else in R3. Here's another problem that we're actually getting into four-dimensional space now. We've got a space defined by A, B, C, D, where A, B, C, D are all real numbers, and they are held together by this equation. That equation has to be satisfied. And yes, we could, and you know, what's going to be on this slide is, yes, we can determine if the 0 vector is possible to happen there. And yes, if you set everything to 0, the 0 vector is in this set. And we could also test to see whether if you add two vectors of this form, it stays in the form. And if we multiply a scalar times a vector in this form, whether it still stays on that same form. Real quick though, I think it would help us make sense a little bit of what's going on if we wrote this in a more standard form. So all I'm going to do is bring everything on the left-hand side of this equation. And then this looks a lot like just a normal plane. You know, if we're allowing A, B, and C and D to be whatever they want. You know, if D was gone, this would look like a plane in 3 dimensions. This one just happens to be a 3-dimensional hyperplane in a 4-dimensional space. So, and since the right-hand side has this 0, I know that this hyperplane will go through the origin. So I'm pretty confident that this will be a subspace, but let's go ahead and take a look at all the little steps along the way. Yes, like I said, the zero vector is part of the set. All you have to do is set all of those letters equal to 0, and you get the zero vector, so that's no problem. If we take two vectors of that form and add them together, using the distributive property down here at the bottom, you can see that we still get a vector of the same form, that we would still be in that three-dimensional hyperplane where we started. So we haven't left the space, and therefore we are closed with respect to vector addition. And here's what it looks like to be closed under scalar multiplication. And the scalar here is k. Yeah, so we're still in the same form as what we started off with. Therefore, this space U is indeed a subspace of R4. And in actuality, and we'll see this towards the end of the slideshow, that yes, this is a three-dimensional subspace of a four-dimensional space. All right, here's another one. If U is defined by this vector, where we've got one S and T, and S and T can be anything, is that a subspace of R3, of just three-dimensional space? The answer here is no. Can you tell why? It's because the zero vector is not in this set. The first component is never going to be 0. It's always going to be 1. And so this does not go through the origin. Yeah, that one doesn't go through the origin. Next one. We have some conditions here. We've got R0 and S in our vector, and R squared plus S squared has to equal 0. Is this a subspace? Well, the condition R squared plus S squared equals 0 kind of means that R and S have to be 0. Since we're working with real numbers here, we could get a little bit squirrely if we were working with complex numbers, but since we're restricted to real numbers, R and S have to be 0 too, and therefore what we're looking at is really just the zero vector. And yes, again, the zero vector is its own zero-dimensional subspace of R3. Here we introduce two very special subspaces, some might call them fundamental subspaces, of a matrix A. We've talked about this before in class. We've at least introduced the terminology. The null space is all of the solutions to the homogeneous system of equations here with the AX equals 0. The vectors in the null space are all of the vectors X that get mapped to the 0 vector under the linear transformation A. So yeah, it's the set of all the vectors that get squished down to the 0 vector. So when you have a non-trivial null space, that means that you definitely have a squishy transformation where, space is getting squashed down and there are multiple vectors from your original space getting squashed down onto the 0 vector. So that's the null space in a nutshell. The column space is really just the span of all of the columns of your matrix A. So, if we were working with a matrix A that had columns A1, A2, and A3, let's say, the column space would just be the span of A1, A2, and A3. And depending on whether those vectors were linearly dependent or independent. Um, that could be a three-dimensional space. If all of those vectors were pointing in significantly different directions, if all of those vectors happen to fall in the same plane, then that span would be a two-dimensional space, and so on. But yeah, the column space is just the span of the columns. All of the vectors that you could, or all of the places that you could get to using linear combinations of the columns of A. We could real quickly prove that the null space is a subspace of Rn. So, and remember, Rn, when you're thinking about a matrix is an m by n object, which means that, yeah, the the vector x here, and when you're multiplying ax together, that vector x lives in n-dimensional space so that the matrix multiplication is defined. So x lives in n-dimensional space, and you're mapping it onto the zero vector in Rm, kind of the number of rows in the matrix. So yeah, you're taking something in n-dimensional space and you're mapping it onto something in m-dimensional space. But here, we're working in Rn because we're primarily focused on those x vectors that get mapped onto the zero vector. And yeah, the zero vector definitely gets mapped to the zero vector under a linear transformation. Vector addition is preserved within a null space. And the null space is closed with respect to scalar multiplication. And therefore we have a subspace by definition. Cool. Prove that if A is an m by n matrix, then the image of A, which this image of A is just another way of saying the column space. And you might think of the word this word image. You might have had that before in an algebra class or something. Talking about like the range of a function, where it lands is what we're talking about when we're talking about the image. We can prove that the column space is a subspace of Rm. And indeed, we've got the zero vector here. That gets mapped to the vector addition is closed, and scalar multiplication is closed. If you have some time, normally during class, I would go through all the four fundamental subspaces of this matrix. It's not necessarily something in the curriculum of this book, but I like to make you aware that really we've talked about two fundamental subspaces so far, the column space and the null space of a matrix. But really, the null space only takes up so much of Rn, and the column space only takes up so much of Rm, depending on the rank of the matrix. There are two other fundamental subspaces called the row space and then the null space of A transpose is kind of the easiest way to say the other one. But if you would like to watch a full lecture, there is a professor named, oh man, I'm forgetting it now. Hold up. Gilbert Strong. Yeah, Gilbert Strong. He is, a professor at MIT. I think he might be retired now, but loved linear algebra and the four fundamental subspaces of a matrix was one of his favorite things to lecture on. And so I put a lecture from, his class at MIT in our playlist on YouTube. And if you have time, go watch it. It's awesome. It's a really, really smart guy talking about something that he loves and that he finds fascinating. And you guys would totally be able to comprehend it. Again, it's not necessarily, you know, required, but I would definitely encourage it. The four fundamental subspaces of a matrix are really cool to, know that they exist and a little bit about how they work. Another type of subspace that exists are eigenspaces. I think I've used that language a little bit already, but basically, an eigenspace is made up of the span of all of the eigenvectors related to a specific eigenvalue. So yeah, you diagonalize your matrix, say, or at least come up with all of the eigenvalues and eigenvectors that you can. Yeah, the eigenvectors that correspond to a given eigenvalue, you put those in a set, you find the span of those eigenvectors. Sometimes, if you if you only have one eigenvector, then that eigenspace would be a line. If you have two eigenvectors corresponding to the same eigenvalue, then those two linearly independent eigenvectors would span a plane. And it is possible to have, you know, eigenspaces of any dimension that's, a subspace of the space where you're working in. For instance, if you were even thinking about like the identity matrix, well, the identity matrix has eigenvectors that are just, the standard basis vectors. So like I hat, j hat, and k hat, for instance, would be the eigenvectors of your identity matrix. And the eigenvalues there, well, there would only be one eigenvalue, and the eigenvalue would be 1. That would be a case where you have a three-dimensional eigenspace, because, under the identity transformation, everything is transformed by 1 in the same, by a factor of 1 in the same direction of where it started. It's kind of a boring transformation, but I just wanted to illustrate that, yeah, eigenspaces can be multiple dimensional. Yeah. So sometimes it's handy to talk about those. Here is a definition of linear combination and span. We have already been using that vocabulary pretty heavily. Linear combination is basically just a weighted sum, and the span is the set of all possible weighted sums that you could take with a given group of vectors. Yup. So, spanning set, yeah, that's great. Let x be a non-zero vector, then the span is a line through the origin having direction vector x. Yup. Okay, we got that. And a span of two vectors would be a plane. Got it. How could you find the equation of that plane? One easy way would be using the cross product. That would give you a third vector. We're working with vectors in R3. So yeah, you can use the cross product to find the normal vector to the plane and then get your coefficients that way. Yeah. Here's basically a vector equation, just in different terms. We're trying to decide whether x is in the span of y and z. And yeah, you could set that up as a vector equation where your weights are a and b in this context. But yeah, that just boils down to row reducing and seeing if you have a consistent system. In this case, we don't. And x wouldn't be in the span of y and z. X wouldn't be in that plane. But if you change x a little bit and make it into a w, then that vector does happen to be in the span of y and z. So that's just really another way of asking the same kind of question as a vector equation. Yeah. Here we go. This is phrased as a theorem. If we have k vectors, x1 through xk, and we have a set u based on their span, u is a subspace of Rn. Definitely, if you're just looking at the span of vectors, the zero vector will be in there, and all of the linear combinations of the vectors will be in there. So it'll definitely be closed with respect to vector addition and scalar multiplication. Part two is if W is a subspace and those vectors are in W, then U would be a subset of W. Or actually a subspace of W is the right way to say that. Yeah, so all that's saying is that if you just take the span of k vectors, that is the smallest k-dimensional subspace that contains those vectors. That's the smallest way to contain them. Yeah, not a huge deal. I don't really want to look at the proof for this. It's just a lot, and it's not super important or helpful. So there's that. There's the zero vector and the addition part, and then scalar multiplication, and yes, we're in there looking at subspace stuff. Meh. Okay. So using that, you can look at this subspace U that we looked at earlier with the A, B, and C, and D. And you can look at it another way and see that it is indeed the span of these three vectors on the right-hand side. In this case, we treated C as a pivot, or like our basic variable. Let's say basic variable. Yeah. And we're letting A, B, and D be free variables. You get this in terms of like a parametric vector form, and A, B, and D are basically your parameters that you're allowed to vary. But yeah, that's where we get the span of those three vectors. And yes, indeed, U is a three-dimensional subspace of R4. That's cool. All right, we're getting close here. We've got X and Y. U1 is the span of X and Y. U2 is the span of 2X minus Y and 2Y plus X. Prove that they are equal. And there is another lengthy proof here, but honestly, it's more important to me that you understand that if we're creating a space U1 based on the span of two vectors X and Y, all of the linear combinations of X and Y are included in that. And so that space is going to be exactly the same as the space over here where we base our space on linear combinations of X and Y. Same space. Because we're both just building off of linear combinations of X and Y. Yeah. To show that these are equal, formally, you have to show that one's a subset of the other and the other one's a subset of the other so that they're equal. And yeah, it's gross and I don't necessarily want to do that right now. So there's that. This again is just telling you that in our book we use e to the j to denote the jth coordinate vector of Rn, which is like the jth standard basis vector. So in 3 dimensions, that's I hat, j hat, and k hat. But when you get up into n-dimensional space, those vectors can get longer. But basically, there's 1, 1, and a whole bunch of zeros everywhere else in the vector. Here we're trying to prove that Rn is the span of those coordinate vectors. And yes, if you take linear combinations, you fill the entire space. That's pretty straightforward. Here we have 4 vectors, and we would wonder if those span R4. Probably the easiest way to do this would be, to row reduce and to see if you get 4 pivots. Yeah, because if you have 4 pivots, that means these vectors are linearly independent, and you can head in 4 different directions and span 4-dimensional space. The easiest way to see it for this one is that, yes, you can get the standard basis vectors just by subtracting, say, x2 from x1 or x3 from x2 and so on. You can get the standard basis vectors pretty easy. But in general, you'd row reduce. And this one, again, the easiest way to show that the span is not 4-dimensional is to row reduce and see that you would only have 3 pivots, and so that you only span a 3-dimensional subspace of R4. And this one's kind of meh. I don't even really want to give it the time of day. But I would like to remind you that, the null space exists, the column space exists. They're not completely new terms, but yeah, hopefully going through this process of looking at various subspaces and showing that they're subspaces has been somewhat instructive. And I do encourage you to take a look at that 3 blue 1 brown video and the 4 fundamental subspaces video from the MIT OpenCourseware. This has been How to Math with Dr. Ian Lundholm. Remember, you have online homework to do, and now you're ready for it. I'll see you in the next one. Bye.